Hello, everyone. In this video, I will be going over the dyadic growth curve. Specifically, I will be estimating the dyadic growth curve in lavaan, estimating both the unconditional growth curve as well as a conditional growth curve. So for those of you who are unfamiliar with growth curve analysis, or more specifically latent growth curve in the structural equation modeling context, essentially it's the idea of estimating a slope or a rate of change over three or more periods of data collection or time points. We're severely limited about longitudinal associations using just two-panel data, and growth curve overcomes that ability to, again, to estimate the change in a construct over a greater number of measurement time points, and it's able to estimate kind of a constant rate of change rather than the kind of a piecewise rate of change that you would have just in two-panel data where you're linking time 1 to time 2 and time 2 to time 3 and time 3 to time 4. Growth curve estimates, again, a single parameter that captures all of the change. And so in this example, we'll be going over changes in marital strain among dyads. So again, this is dyadic growth curve. So what we're going to be doing is estimating those rates of change among dyads, and in this case, heterosexual couples. So let's dive into the syntax. So the first is create our model object. And again, for demonstration, I have some previous syntax I'm not going to go through here. It's just univariate growth curves. But I have my data, and I'm using Haven and lavaan to estimate the dyadic growth curve. So I'll go back down to the unconditional dyadic growth curve. And so what we're going to do first is estimate just the means and the slopes for each dyad members. And what that means is that there are no predictors in the model. So you can kind of liken it to identifying the factor structure in latent variable models before estimating the regression coefficients among the latent variables, right? So you want to first establish that there is good measurement, and then you move on to your full structural analysis. What's a very similar process here in latent growth curve. We first want to estimate and establish that there is a rate of change over time that is occurring before moving on to using that rate of change to predict a distal outcome, or perhaps even be predicted by a variable. So first, we are going to estimate the female intercept and slope. So I have IF and SF to indicate intercept female and slope female. And so for the intercept, you constrain all of the loadings to be 1. All right. So you constrain, you do so by using the 1 star as telling lavaan that I want this factor loading to be constrained to be 1. And so you're going to do that for each of them across all the time points. All right. And this will be interpreted as the average levels of the construct, which is marital strain at wave 4 for women. Right, so that's how the intercept latent factor will be interpreted. Now we will set the slope equal to the time between the waves, and we start with 0. So technically, this is wave 4 within the data set and wave 1 within our model, but we are going to constrain that to be 0 because that allows this interpretation of the intercept to be kind of what I just explained that it was. If these slopes, these slope loadings, I should say, had different values, then the interpretation of the intercept would be slightly different and slightly less meaningful. And so the survey was administered annually. And so what that means is that every single year, both members of the dyad came back and came back and came back and came back over time. And so we are going to use those 1-year time lags to estimate the loading. So starting with 0, we're going to have fix that to 0, and then they came back 1 year later, and so that would be 1, and they came back 2 years later, which means we'll constrain that to 2. Let's say, for example, we had uneven measurement time points for whatever reason, say COVID. So let's say we had wave one in 2019, wave two in 2020, and wave three in 2022. So we missed 2021. But we still kind of assume that there is kind of a linear growth, that even though we don't have data in 2021, um, for due to COVID, we kind of say we would imagine that there would still be a slight increase in the mean levels of our variable of interest, and that would be in line with previous levels of change. The same, so it'd be the same rate of change as between 0 and 1 and 2. Right. So we're going to kind of assume that we don't have that data. So what we can do is that we can actually fix this to be 4 or 3 actually. Right. So we're kind of presuming, and I'll do the syntax really quickly. Um, we're kind of assuming that there's a linear rate of change, you know, across these 4 waves now. But this wave, this is the COVID wave where we didn't actually measure. We're kind of assuming it's on the same trajectory, right? So we're assuming that, again, the distance between 0 and 1 is the same as 1 and 2, which is the same as 1 and 3. So even though we didn't measure it, we're going to kind of assume that it's there. So we can actually, again, have unequal time points. As long as we have 3 waves of data, then growth curve analysis would be an appropriate analysis, or I should say one of a possible many analyses that would be appropriate if there's underlying change in your constructs of interest. Right. And so again, so setting the factor loadings to 1 for the intercepts, starting with 0 and going in a linear fashion with 0, 1, and 2, we have created the 2 latent factors for the female growth. So next, we are going to fix those means of the observed variables. So wave 4, wave 5, wave 6 to be 0. And so we're kind of pushing mean information up into the latent space. And so what this is doing is this is going to allow us to estimate the latent means of the intercept and slope factor. All right. And you'll see why this is important in a few moments, but briefly, latent means are going to be what tells us how quickly, or perhaps not quickly, that females are changing in their levels of strain over time. All right, and so you'll see, I'm going to scroll down, I'm using the growth function in lavaan. You do not need to actually specify this. This is a default in lavaan. I am doing this for illustrative purposes, and perhaps you're using the sem function, in which case you would most likely need to specify the intercepts to be 0. All right. And so the exact same syntax is created for males. The only difference is that instead of, again, female growth, we're estimating male growth. And so again, I literally copied and pasted the syntax and just changed these the F's into M's because again, it's the exact same. We want to estimate the exact same thing. We want to estimate an intercept for males, or what is their average levels of marital strain at time 1. And we want to estimate a rate of change in male strain over time. We want to see, does it increase or does it decrease? Right. And as you can see here, I have also set the means of the observed variables to be 0. So in the dyadic growth curve, and I'll actually pull up an image of it. So this is what we are estimating. So this one down here would be the male factor, these 2, and then up here would be kind of the female factor. We're using 3 waves in our lavaan syntax, but this has 4 waves, but essentially it's the exact same thing. And then we are estimating change for both members of the dyad, and then we want to estimate to what extent do they change together, right? So as women's slopes of marital strain kind of increase over time, what happens with male slopes? Do they also increase, or perhaps do they decrease? And that's a question that we'll be able to answer by estimating the covariates. And then for those of you who are familiar with the actor-partner interdependence model, we account for interdependence through, you can kind of view these covariances as partner effects in a way, actor and partner effects. and also through correlated residuals. So these residuals are essentially unexplained associations between male and female strain at each wave that is not accounted for by their levels of strain at time one or their growth process over the study period. So moving back into lavaan, we are going to estimate those covariances right here. So we have the intercept of male with the slope of male with the slope of female plus the intercept of female. We have the slope of male with the slope of female and the intercept of female. And finally, we have slope of female with the intercept of female. And again, there are likely unexplained there's unexplained variation that is accounted for, that is shared by being in the same dyad, by dating somebody. And so we need to account for that lack of completely independent information. So we're going to correlate those residuals as I had shown you in the diagram. Without accounting for these residual correlations, we are going to have biased covariances and perhaps even factor loadings, standardized factor loadings in the growth curve model. And then we're also going to potentially have biased standard errors where we have less unique information that we think we actually have, which results in a type 1 error. And so we can go ahead and we can run this. And again, you'll see just very basic output requested. So we have our fit statistics. We're using robust maximum likelihood. We have some missing data. So we're doing missing equals ML. And then we want our summary. So you'll also notice that because we are working with latent means in growth curve modeling, that we actually want to estimate those latent means, and they're actually of substantive interest to us, unlike many other SEM models. So typically you'd want to estimate that by mean structure equals true, but in lavaan, by using the growth function, that is estimated by default. So you don't have to tell lavaan to request the means or the intercepts. Um, and so you will see that we actually got an error message. So if you get an error message like this in lavaan, then it probably means that there's a syntax error, or perhaps that you actually haven't set your working directory, which is exactly what has happened here. I had not set my working directory previous to the analyses. So one of the things that is both kind of great about lavaan and also kind of frustrating is that you need to set your working directory each time. But one of the benefits is that if you actually open up your lavaan syntax like if you go into the file folder where you're storing your lavaan syntax and you double click on it, in your data files in that same folder, it will set your working directory automatically. But if you just open up R, then it by default sets it to, I think you can even set the default of what the default folder is. And I had just opened up R the old-fashioned way without closing in on the syntax or opening through the syntax, and I just opened R through the icon on my desktop. And so that is the reason that we are getting that error message. And as you can see, there is my SPSS data file, and there's my lavaan syntax growth.r. So we set our working directory. We scroll down to the unconditional dyadic growth curve, and we'll see whether or not it works. So we'll need to read in our data file, and using the Haven package, and then there we go. All right, so the dyadic growth curve model, we have 4 degrees of freedom, and it fits the data really, really well. A very small chi-square, which means that the 4 restrictions that we are placing on the model are not significantly harming our ability to reproduce the variance covariance matrix. And as you can see, with such a small chi-square, not surprisingly, our CFI and our TLI are behaving exceptionally well. They're both at their max values. Your RMSEA is going to be 0. And more importantly, is we have a really tight confidence interval around the RMSEA from 0 to 0.015. And we have a 99.6% likelihood of having our RMSEA being below 0.05. And so we will scroll down. And so there's a couple of things that we will kind of want to look for. With the unconditional dyadic growth curve model, essentially what we're trying to accomplish is estimate the rate of change and the average starting point for both men and women, or both husbands and wives in this example, to see if there actually is change, right? So one of the ways to establish that, and it's not a definitive, purely causal way, but it's a way to kind of get a sense of what's going on, is look at the standardized loadings in your data. Where if you see for the intercept factor, all of these are kind of huddled around 0.80, 0.81, which is good. We want them to be all huddled around and have roughly the same effect size. We want to have the same standardized regression coefficient, because again, the intercept has everything fixed to 1. And so that would say we want the intercept factor to have an equal influence on all of the 3 observed time points. And so if this is 0.90 and this is 0.70, that means there's an unequal influence happening and there's something funky going on, and perhaps growth isn't what we need to be doing, or perhaps we have some outliers that are really messing with our ability to effectively estimate the intercepts, or perhaps we had ran into an estimation error, or whatever it is. But we really want these variables to be closely related together. On the other hand, for the slope factor, we want these standardized variables to be proportionately different to the factor loadings that we constrain them to. So the difference between 0 and 3.02, 0.32 is 0.032 is exactly 0.032. And so the difference between 0.032 and 0.059 was it 0.288? So that's really, really close. And if you estimate a growth model where you have 0 and then you have 0.302 and then you have 0.80, then you know that there's something funky going on, because there's something going on with the way you're coding time, perhaps. But there's something kind of not quite right. That will probably show up in your fit statistics, although that's, again, not necessarily a causal relationship between the two, but it's a good way to kind of check to be sure that you're estimating things, right? Because if we're estimating a linear change in something, then we would expect these standardized loadings to be roughly linear, where the rate of change is constant. That 0.302 and that 0.288, those are roughly constant rates of change between wave 1 and 2 and 2 and 3 respectively. And we do that for both males and females, just to get, again, a sense of our data and kind of figure out what's going on with our data. All right, so next we have our covariances. And so what we have here is our intercept and our slope for males. We have our slope for females with our intercept for males. We have our intercept for males with the slope of males. And finally, we have the slope of females with the slope of males. We only have one significant covariance, and when you're doing dyadic growth curve, this is almost always significant. So essentially what this is telling us is that levels of marital strain at time 1 for men and women are correlated at 0.388. So that means where men start and where women start is fairly and significantly correlated with one another. It's not exceptionally strong, but there is a fairly significant relationship. But you'll see in other places, there's not really a whole lot of significance. Our effect sizes, aren't that small, especially right here. But as you can see, our standard errors are actually fairly high, which means we don't have a lot of precision in estimating the covariance between the intercept and slope for men and the slope of men, the slope of women and the intercept of men, right? And so what we'll do now is actually scroll down to the means. And so what we are going to do is look at under intercepts, look at the factor means, because again, we are estimating those. So the intercept for females, its value is 10.947. Again, what this means is that this is the average score for female strain at time one in our study among all the 627 women that are in our analysis. That's going to be the average score of strain. And for men, we have that same interpretation, but our value is 11.256, right? And what we can do is actually estimate whether or not these are significantly different from one another, but that will be later on, right? We also have, and those are significant. That's another important feature, right? So there's a significantly different from zero. And essentially that tells us that the levels of strain are significantly different from zero, which means strain exists in that relationship, all right? And so next we'll look at the slopes, right? So we have the slope for females and the slope for males. And so what we see is that this is the mean of the latent variable, and it is not significantly different from zero. And we have the same thing for males. We have a slightly smaller or larger slope, and it's approaching p equals 0.05, but it's not quite there yet. And so what that tells us is that there is a rate of change. There is actually a decline in marital strain over the study period, but it is not significantly different from zero, right? So it's essentially like a non-significant slope or regression coefficient in your OLS regression, right? It's kind of the same idea across, again, more than 3 time points where in a regression you can only assess up to 2 time points, right? So that is non-significant. So there's not really much change that is happening for men and women across the study period in relation to strain. So now we're going to scroll down and we're going to look at variances, right? So again, every latent variable needs a mean and a variance. And now, as opposed to many other SEM models like path analysis, those means and those variances are of great interest to us. And we see that all of the variances are significant. So, well, how do I understand that with some slopes being non-significant? Well, we can have a non-significant slope for men. We'll use that as an example. So on average, for every male in the sample in our analysis, they are getting a value of 0.083, right? As a group, that's the overall mean. But when we have variance, and specifically a significant amount of variance, that means that some men are going to be really, really close to that 0.083. All right. But other men are probably going to be much, much, much further away. Some are going to be at 0.09 and 0.10 and 0.11 and 0.20 even. And some are going to be 0.05, 0.03, 0.01. Some might even be negative. So that tells us that not every male has that exact same value or a value really close to that 0.083, it means that there's male to male differences in the rate of change over time in this sample, right? So if this was the variance was non-significant and we had this, that means this negative slope is not significantly different from zero, and it's a constant or can be treated as a constant where there's no variation. That literally means that 0.083 value applies to every single male in that sample. But when the variance is significant, we can just say that's the 0.083 is the average, but there's variability in that. All right. And so the same thing can be said for female slopes. So even though it is not significantly different from zero, Some women are really, really high in changes in strain. Some women are really, really low in changes of strain, particularly declines in strain. And some are going to be clustered perhaps around the mean, right? So again, when you're doing growth curve modeling, latent means and latent variances are of the utmost importance. So there is kind of one thing that I want to return to is we have some covariances here. And the covariances, when you were thinking about latent means, could be exceptionally difficult to kind of interpret. And it might take your head a little while to wrap your head around it. It certainly took me a little while to finally understand kind of the proper interpretation. So we're going to use our example. So our latent means for the slope factor is negative 0.039 and negative 0.055. So that means there is a decline in marital strain for both men and women. Specifically for men, it's 0.055, and for women, it's 0.039. All right, so we're going to scroll back up here. That's really important. The latent mean is really important. So here we have a slope. So this is going to be negatively correlated. And we also have a slope and an intercept. This is going to be positively correlated. All right, so when we have a negative slope, right, and we have a positive correlation, that means that men who have higher values, a 1 unit increase in male intercept or the average level of male strain over time is associated with a 0.02 unit decrease in changes in or declines in strain in female strain over time, right? So when you have a positive correlation and a negative slope, that indicates that that there's a deceleration. So essentially, again, the idea is that when the more male strain, the higher levels of male strain at time one, that means that there's lower levels of increase or decrease or yeah, lower levels of decreases in female strain over time. Okay. And so that would be the interpretation of a negative or a positive correlation with a negative slope. So now let's go over to a negative correlation with a negative slope, and we're just going to pretend for funsies that these are significant and that our p-value is not 0.99. So what we would kind of interpret here is that, if this was points, let's say 2.0, then a 1 unit kind of increase in the declines of female slope would be associated with a, let's say, again, 0.20 units decline in male slope. So when you have a negative mean, because again, going back down here, both of these means are negative, and you have a negative association, that means there's going to be it means there's going to be accelerations or steeper declines in the association. All right. But on the other hand, let's say we had kind of a positive mean. Let's say there was increases in strain over time, and we had a positive coefficient, like this one right here. That means that that there would be a covariance where the higher the levels of male strain at time one was associated with steeper increases in declines in the female slope. So there's greater increases in strain over time among women when men are higher to start with, right? And so the opposite would be true if we had a negative correlation. So let's say we had a positive mean but a negative kind of correlation. So that would mean that a kind of a 0.01 unit increase in the slope for males leads to a 0.001 unit decrease in the slope for females, and that would be interpreted as when the male slope increases, that means the female slope increases, but at a slower rate. All right. So that is something that can be extremely, extremely difficult to kind of wrap your head around. And so I have a slide that I absolutely kind of stole slash borrowed while giving the appropriate credit to Todd Little, that this really helped me wrap my head around it. Is that when we have, and again, this applies for covariates, this applies for intercepts, this applies for anything that we are doing when we are predicting slope variance, is that when the sign of the mean and the sign of the regression coefficient are the same, that means there is either an increase or an acceleration in the increase or decreases of that latent variable. When the signs are matched, it means it's going to be more increasing or more increasing depending on the sign. If it's positive, it'll be more increasing, and if it's negative, it'll be more decreasing. However, if the signs are mismatched, so if there's a positive mean and a negative association, or there's a negative mean and a positive association, that means it's going to be less increasing or less decreasing, right? And if you have a positive slope and a negative coefficient, it's going to be less increasing. So that slope gets smaller and smaller and smaller the more and more that negative relationship with the covariate goes up and up and up. Likewise, when we have a positive association with a negative mean, that means that that mean is getting pulled closer and or that slope of the latent variable, excuse me, is getting pulled closer and closer and closer to zero. All right. So that's kind of how I think about it. If you're a little bit more visual, if you have a positive mean, so this top box right here, all right, I'll highlight it right in here. If you have again, a positive relationship, it goes up and up and up. But if you have a negative association with a positive mean, that negative covariate has a negative correlation with your positive mean, that you can think about it as pulling that regression line down closer to zero. So it goes from 0.3 to 0.1. So that negative association is literally kind of hanging on that. View it as like a kid hanging on to kind of like a seesaw, and it's pulling that down towards zero. Likewise, you can kind of view it with a negative slope and a positive correlation, as that slope is getting pushed up towards zero. All right. So when you have opposite sign regression coefficients and latent means, you can think about the slope values getting closer and closer and closer to zero. Whereas if you have the same the sign of regression coefficient and same sign as the latent mean, then you can view them as getting pushed further and further and further away from the slope being zero. All right. So again, it can take your head, 5 or 10 or 15 or 20 or 30 or 100 different times thinking about it, like me, in order to get this. But once you get it, it's kind of in your system, and it's something that does make a little bit of sense. But it does get you. It does take you a while to kind of wrap your head around the different interpretations. But I really like this diagram that Todd Little used in his longitudinal SCM class that I took several years ago. So moving back over to lavaan, we can take a look at R squared all over, although it's not, again, all that meaningful, at least at this point, because again, we're just estimating the amount of variance accounted for by the intercept and growth factors in each partner. All right, so what we can do next is we can constrain the residuals to be equal across time and within partner, within and between partner. So first, we're going to estimate or constrain the residuals to be equal for men. All of their residuals are going to be the same, and for women, all of their residuals are going to be the same. Again, this is called sometimes the stationarity assumption. And so all of this syntax up here is going to be exactly the same. The only thing different that we're doing is now we are throwing parameter labels on all of the male strain residuals and all of the female strain residuals. And so I've just donated, residuals are lying in your theta matrix. So I just use theta 1 to constrain all of them to be equal. So again, if your variables have the same label before it, that tells lavaan constrain it to be equal. All right. And so what we can do is test whether or not this is a tenable assumption, right? So, and we'll do that through using a likelihood ratio test or a chi-square difference test. So we can go ahead and we can run that, and we can see that we get, we have 4 degrees of freedom, and our p-value is 0.07. So that means imposing restrictions on the residuals across time within person, but not between people. They're not the same. That does not cause significant harm to the model. So that makes the model a little bit more parsimonious. And then we can say with more confidence that all of the observed variables are kind of affected equally by the slope and intercept factor. There's the same amount of leftover information for each person across those 3 time points. So the error variance for strain at wave 4, wave 5, and wave 6, or wave 1, 2, and 3 for us, is identical, right? So the same amount of unexplained information is present. So what we can do here is now do the exact same thing. So all I did was copy and paste the syntax from above, and I constrained the residuals to be equal across over time and across partner. So I am constraining the male residual at wave 3 to be identical to the female residual at wave 1, right? And all the other possible combinations of residuals. Right. And so again, this is an even stricter assumption. Not only are we saying there's the same amount of unknown information at each time point within person, that is the same across dyad member. That is the same for men and women. And what we can do here is we will conduct another likelihood ratio test, and we'll compare all 3 models with the residuals completely unconstrained, with the residuals constrained over time, but only within a person, or the residuals constrained over time and within person. So everyone's the same. So we can go ahead and we can run this model and see if that's a tenable assumption. And we see here that it is. So adding in those residuals across partner doesn't significantly decrease the model data fit. So again, this is a more parsimonious model. And this is actually a way to test indistinguishability. We need to do a few more things to get complete indistinguishability, such as constraining the means and the variances of the 2 latent variables to be equal. But this is beginning to tell us that our men and our women are in a lot of ways the same, right? All right, so what we're going to do next is we're going to keep all these constraints, but you will see I am now going to constrain the intercept and the slope factors to equality across persons. So you will see the intercepts are constrained to be equal for men and women, and the slopes are constrained to be equal across men and women. All right. And so this will tell us whether the rates of change differ across men and women, and whether where men and women start significantly different from one another. All right. So essentially, this is testing gender invariance of the intercept and of the slope. So we can go ahead and we can run this model, and again, we'll conduct a likelihood ratio difference test comparing this model to the fully constrained residual model that we just ran. And we can see here that boy, oh boy, does constraining the means only, um, uh, does that hurt the model? So that's a highly, highly, highly significant chi-square, which means that the intercepts of constraining the intercepts of the means of the intercepts and slopes, excuse me, to be equal across men and women is not a good thing. All right, so that means there's significant harm done to the model. So here, if you'd like to go further and you want to know whether or not it's, just the slopes, just the intercepts, or is it perhaps both, then you would just you'd freely estimate one of those and you constrain the other to be equal and just conduct an additional series of likelihood ratio tests or chi-square difference tests. All right. And so you could also do that with your variances. So I didn't do this in the model, but let's say you were interested in constraining the variances to be equal. Um, you could constrain variances to be equal. So you'd have the intercept for male, and then you have the intercept for male, and then you could call it, let's call it, psi 10. All right. And do that. And then you could do IF, and then you could do psi 10 times, or asterisk, I should say. And you have SM. Um, and then you could do psi 20, and then SM. Then you could have SF. Oh, whoops, this should be two tildes for variances. And then they could do psi 20 SF, and lavaan is case sensitive. And so this would actually constrain your variances to be equal. So this would, if you were to run this in addition to this would give you again a 4 degree of freedom likelihood ratio test. Or again, you can do this one by one, which is actually what I recommend for best practices. So you can actually know which parameters are actually different, because you could have one honking difference and three non-significant differences, but you could still get an omnibus test that indicates significance, and you're kind of presuming that all four are significant when only one is. I kind of think of it in an analogous way uh, to the omnibus test in ANOVA. All right, so we really care about the mean difference between groups 1, 2, 3, and 4. The omnibus test just tells us that there are differences, but doesn't tell us where, and it doesn't necessarily mean that there are differences between every single group. So again, I'm a big advocate for, let's test those post hoc differences, use Tukey's, and in the SCM, kind of equivalent is that is constrain one set of parameters to be equal across time and conduct a series of likelihood ratio difference tests. All right, so the final model that we are going to look at is what's called the conditional dyadic growth curve model. So the conditional dyadic growth curve model now introduces covariates into the model, or if you want to call them predictors or exogenous variables, whatever term kind of floats your boat. We can do that. All right. And so what we're going to do here is we are going to have relationship length as a between dyads predictor. Right. So I say between dyads because relationship length, if men and women are coming from the same relationship, that variable will have the same value for men and women. Right. We could also do kind of more mixed variables, like attachment, for example. But here we're just using relationship length. And so we have, again, the exact same model as before. All right. And so you'll see everything else kind of being the same. The only thing that I have done is added in these structural pathways where I'm using relationship length and observed variable to predict intercept and slope variance. So you'll see I have them labeled. That's for that's would be if I wanted to test. Perhaps there's a distal outcome, which you could absolutely test, and you could actually examine your latent intercept and your latent slope as mediators from relationship length to say, I don't know, a relationship commitment, for example. And so you could do that. So that is kind of where you would use these parameter labels. But in this current model, that's not necessary. All right. And so again, they're not the same labels. So again, it won't affect your model in any type of way. But essentially, we want to know by inserting relationship length as a predictor whether or not the longer you've been in a relationship, does that influence where you start in terms of strain for men and women? And does that influence perhaps how much you change over time? So going back to our previous models, um, I'm actually going to pull up the old output just for a second because I'm going to do something you shouldn't, or potentially shouldn't, depending on kind of where you're at. Uh, Previously, we had no significant mean differences, right? So in our intercepts, so go all the way back up here. So we had the slope for men and women being non-significant. And so that means it's pretty much, there's not a significant increase or decrease. So we probably wouldn't want to predict something that's non-significant. Why would you want to predict a non-significant slope? So I am doing this purely for demonstration purposes, but in order to for the dyadic growth curve to be really useful for you, you would want a significant mean. You want this value to be below 0.05, which means there's significant decreases in strain for men and women, and you would want for there to be a significant amount of variance, right? Because if the variance is non-significant like it is here, what that tells us is that that slope is a constant, that again, um, that decrease, again, for men, it's non-significant. So for men here, that negative 0.055, that applies to every single male in the sample. There's not a significant amount of variation happening, right? So knowing full well that I should not estimate this model, I am going to estimate this model purely for pedagogical purposes. And so again, we're going to estimate the effects of relationship length. So we can go ahead and we can run this model. And we have a really good fitting model. So our model is actually reproducing the characteristics of our data really, really well. With with really good CFI values, really good TLI values. RMSEA is really good. This 90% confidence interval is really good. The p-value of the RMSEA being below 0.05 is really high. So we're doing really, really well at reproducing the characteristics of our data. Unfortunately, our hypotheses are just not supported. Relationship length does not differentiate dyad to dyad to dyad in terms of where they start in terms of average levels of strain for each partner and how each partner changes over time. But we are going to interpret them just to, again, get some practice. We're going to interpret them as if they were significant to get practice in the really befuddling and can be confusing way of interpreting slope associations with slope coefficients. So again, we have means actually, in this model, and again, this would be, again, kind of a sign of a red flag, that our slopes have actually now turned positive. So there's something funky going on in our data, but we're going to pretend, again, for pedagogical purposes only, that these are legitimately positive slopes. And so that means strain is increasing over time. Right? So that's all that that means. So that means, so with slope increasing for both men and women, right? So the S, right? Um, that means for relationship length. All right, so it's going to be positive and it's predicting the intercept. So the longer you've been in a relationship, the higher your initial levels of strain are for women. And the same is true for men. So for a 1 unit increase in years you've been together results in a 0.059 and a 0.065 respectively unit increase in the male and females um, starting point in levels of strain. All right, so we have a positive slope, right? So recall we have a positive slope this time, and we have a negative association, which means that we are going to be decelerating, right? And so we have a positive slope, which means that we are going to be that strain is increasing. So that means we're going to be decelerating strain. So this would be interpreted as a as as um, as couples have been together for more and more and more years, that means that the changes in female strain decrease. All right. So there are less pronounced increases in strain. Again, that positive mean over time, and less pronounced is coming from that negative sign. Okay. And we have the exact same interpretation for men, where a 1 unit increase in a relationship length leads to a negative 0.028 unit decrease in the acceleration or in the increase of male strain over time. So those would be the interpretations. Again, it can be exceptionally difficult to kind of get your head around, but the more and more you practice, the easier and easier it gets, and it becomes kind of like riding a bike. Again, my favorite way of understanding it is if the signs are the same direction, regression coefficient and latent mean, then I know we're accelerating. And if they're opposite, then I know we're decelerating. Either we're decelerating in increases or we're decelerating in decreases. We're coming closer towards that slope being zero. All right. So there are several other extensions of this, the dyadic growth curve. You can throw distal outcomes in there. You can test full indistinguishability, which I've kind of alluded to, but I didn't explicitly test. You can test the slope and intercept as mediators. You could look at interactions between slope and intercept using latent variable interactions like latent moderated structural equations or Bayesian estimation. Lots and lots and lots of flexibility, but we are going to kind of end here. Hopefully this has been helpful to you, and hopefully you understand growth curve and specifically dyadic growth curve just a little bit better. All right, thanks so much.